Good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome my colleague and collaborator from London, but this is London of Western Ontario, not London, England, Canada, MASOUD KHALKHALI. We have known each other for what, like 25 years or so? That's quite a long time, a quarter of a century, isn't it right, MASOUD?
Yes, yeah. That's absolutely correct. Absolutely correct.
And I'm very happy that he is a semester opener, or actually academic year opener, and he will be bootstrapping us with Dirac ensembles. MASOUD, the floor is yours. Take it away.
Okay, thank you so much, Piotr, for your kind and very nice introduction. I should also thank organizers for inviting me. This is a great opportunity. I much appreciate that. I much appreciate it. Thank you so much to all the organizers and you, Piotr. Yeah. So, yeah, okay, so this is the title. So this is a bit of, I would say, kind of ambitious talk because I tried to summarize contents of 4 papers, more or less, that we have written so far. But let's see how it goes. But then when Piotr said an hour and a half is given, so perhaps one can try. Okay, so so let's see. Why can't I move my screen now?
Your usual cursor should move the screen, no problem.
It doesn't. Oh, no, it works. Okay, thanks. Sorry.
Yeah.
So as I said in my introduction, it's of course very interesting to find or to see connections between non-complex geometry and other areas of mathematics. So this venture sort of started like, I would say, already 5-6 years ago. And there has already been one big meeting in Münster. This was organized or co-organized by Gaëtan Bourreau, Hannah Markwick, Raimar Wulkenhaar, and myself. And there is another meeting planned next year, Fields Institute site in China, not Fields Institute, I'm sorry, the Pacific Institute site in China, in Chengdu, to do the second part of the meeting. So there is something happening, and I'll try to give you a kind of, yeah, some elements of the story. So this is the poster of the Münster meeting. It was drawn by Gaëtan Bourreau, a co-organizer. So as you can see, many elements of the 2 subjects are here. There is non-commutative residue. There is, yeah, these kernels for topological recursion. There are these, yeah, there are these resolvent, tracial resolvents of matrix ensembles and so something, and they're trying to connect. On the left-hand side, there is only the torus, but on the right-hand side, there are a lot of algebraic curves you can see. So this is kind of a dream. So now let me start. Perhaps you have heard this slogan, or you have seen it maybe on bumper stickers, some cars, that physics is where the action is. What of course this refers to is, well, I mean, you can interpret the slogan in different ways, right? But I take it as saying that the action principles of physics are fundamental things for classical physics, at least. So you have classical Lagrangian action, while phi is fields, and M is the space where your fields live on, and these fields can take values in another manifold or vector space, or could be sections of a vector bundle, or all kinds of things phi could represent. And this action is just like that. Is you just integrate. If you know the Lagrangian, you integrate with some nice boundary conditions, you get the action. And most of classical equations of motion in classical physics are Euler-Lagrange equations for this action, actions that are written like that. So Newton's equation, Maxwell's equations, Einstein equation, Dirac and Yang-Mills equations are all Euler-Lagrange equations. By the way, I mean, something interesting as a historical remark, I should say that Lagrange himself did not believe in this, sort of critical action principle. He thought this is a bit of, kind of superstitious and a little bit, he saw some elements of some theological elements in this. And of course, he was a man of enlightenment, so he didn't want to put physics based on some sort of kind of principles like why nature is always so wise to decide like that or things like that. So he derived actually the Euler-Lagrange equations from different principles, but that's a side remark, a historical side remark that we can discuss it another time. But anyhow, the equations are in the hands of Hamilton and Jacobi, turned out to be the way that it passed to us as exactly what we see them today. Okay, but in quantum mechanics, you want to quantize this action, and we have Feynman's recipe for quantizing the action. And the recipe says that if you want to construct average values of observables of your theory, you have to integrate e to the I over h bar of the action against all fields. There is a fictitious measure on the space of all fields, which we know that does not exist. And your observable is a sort of function on that space of fields. If you are lucky, you can calculate that integral, and there you go. That's Feynman's recipe, which has a lot of justifications, at least in finite dimensional discrete cases. So this is a very bad divergent integral, but yeah, I mean, physicists can regularize and renormalize this and get reliable values for Yang-Mills action of the standard models, for example. But even the most daring physicists, most courageous, inventive of them, could not make sense of this thing in case of gravity. Well, the gravity action is what I wrote down there. So this is the so-called Einstein-Hilbert action. So for a metric, now your dynamical variables are metrics on your background space-time, and R is a scalar curvature. You are integrating against the volume form that's given by the metric. Now this is non-renormalizable. I mean, this integral is non-renormalizable. There is a book, by the way. Feynman has spent a year or two, maybe more even. But there's a book that he kind of records his efforts in trying to make sense of this integral. At the end, it's clear that he had given up. So even Feynman was, gave up against this difficult problem.
But you mean this first integral, right? This with O.
Exactly, the first integral. Oh, absolutely. The second one is classical thing, and if you minimize, if you apply Euler-Lagrange equations, you get Einstein field equation, which is now about that actually. So I cannot resist quoting Einstein and Hilbert. So he says Hilbert's approach to physics is childish in the sense of a child that recognizes no malice in the external world. So this is a letter Einstein wrote to Hermann Weyl immediately after this sort of that contentious 1 month activity and sort of competition between him and Hilbert. Okay, it's a long story, but anyhow, Einstein was not very happy at the end. Eventually they made up, they became good friends again. But Hilbert also had his own things about Einstein, said, okay, so every boy in the streets of Göttingen understands more about 4-dimensional geometry than Einstein. So, of course, he goes on again in the same quote, said that, but physics is really, done by physicists. So this is, even Hilbert acknowledged, of course, Einstein's not, Einstein's take on physics. Anyhow, so this is just what it is. Of course, from non-commutative geometry, we have this Connes-Chamseddine action principle. So the idea is to replace the action, which is integral Lagrangian, by something which is a spectral. So you have your action, which is S given by this sort of a classical thing now is sort of a trace of an operator. So you have to modify, you have to sort of tame your operator by introducing a cutoff and also introducing a nice function so that it becomes traceable. So once it becomes traceable, I mean, existence of F is because cutoff is just too brutal. I mean, it creates very difficult terms. If you smoothly do the cutoff, which is by introduction of F as well, then you can use heat kernel expansions to get nice results. So you get the classical actions like Yang-Mills and Einstein, and if you do it before fermions, then the Dirac action also emerges from this. So this is a very successful proposal, but it's not second quantized. You have to still second quantize this, and that's the question.
I have a question, MASOUD. Can you give an example of such a positive function F? How should we think about it?
Take for example, exactly. Yes. Take for example Gaussian e to the minus x squared. Perfect. That's perfectly well. That will work perfectly. Well. Should be even with nice decay at infinity. So that right. Okay. Mm-hmm. So that's the thing. Then, as I said, the question is how to quantize. If you want to go with the spectral action, it seems it's this Hilbert space of the theory is really one particle state. So you have to generate 2 particles, 3 particles. So you have to do some sort of focus space of this spectral triple. So there are some ideas, but nothing very concrete has happened there. But the alternative approach would be just to be very modest and start with very modest goals. That is, just to start with finite non-commutative spectral triples. I mean, that's what. So to modify, to sort of motivate the definition that's coming next. So let me just recall, although there is no need to recall this for this audience. This distance formula, well, for a Riemannian spin manifold, the distance can be read from Dirac operators, so in a dual manner compared to the classical formula that you see here. By the way, do you see my cursor moving?
Yes.
Okay.
Yes.
Okay, so that's very good, right? So this is the classical dual formula you all know. So then the idea is that, okay, so these Dirac operators, we can take them now as perhaps dynamical variables instead of metrics. And instead of trying to integrate over a space of metrics, maybe we should integrate over a space of all Dirac operators, provided they are finite dimensional, and see what you can do with that. And that's this is not quite correct, this sort of finite example I'm giving here, but it's almost correct. So you can keep this in mind that the operator D, the Dirac, is like anti-commutator with a Hermitian matrix. Usually, in general, you have to tensor your Hilbert space, which is just like Cn, well, it's actually a space of matrices by some Clifford algebra, by some space where Clifford algebra is acting on. I'll give you exact definitions, but this is just something you can keep in mind. Then there is this model that was proposed by Barrett and Glaser, by John Barrett and Lisa Glaser a few years ago. The model is that, okay, let's take the partition function of, say, quantum gravity, which in one form should be just integral on this left-hand side. By different partition function, you start with a finite spectral triple, a real, simple, finite dimensional spectral triple. And let's look at over a space of all Dirac operators like that and see, hopefully this will be sort of a kind of toy model for quantum gravity. That's
Sorry?
Sorry?
May I have a question?
Yes.
So the algebra is fixed?
Yes, well, the fermion space is fixed actually, yes. Only the operators are changing, right? So it's like against a fixed background, yes.
Okay, thank you.
Okay, So the simplest type of action, which is sort of non-trivial, is a quartic action. Well, S of D is G trace of D squared plus trace of D4. So the coupling constant in this case appears in front of trace of D2, not in front of trace of D4, but that's, okay, so that's, let it be. Okay, so that's one of the proposals. And then what emerges in at least simplest examples, if you try to write your D in terms of that Hermitian matrix that defines D, you get a kind of difficult term or difficult terms like this in terms of the H, the Hermitian operator that defines your Dirac operator. So these are much more complicated than terms that people in random matrix theory are used to or usually work with. So Barrett Glaser studied these models solely with Monte Carlo Markov chain methods. And when John gave this talk in Primitive Institute 5-6 years ago, I was there, and I was naive enough to think that, okay, I can do something with it because, well, there is something called random matrix theory, and they have a lot of techniques. So why don't we just use random matrix theory and solve these models and see if we can get the results that they got? Well, this turned out to be very difficult because I just almost didn't know nothing about random matrix theory except very, very basics. And so these models that emerge from this non-quantum geometry are exactly on the frontiers of random matrix theory literature, if you want. So one question is, what is the nature of unitary invariant functions? So Hn is always in this talk a space of n by n matrices. So they are going to be polynomial in trace of H, trace of H2, trace of Hn in general. Most of random matrix theory literature says this is in polynomial or a function in trace of H. Or actually the other way around, trace of a polynomial in H, which is not strong enough to capture all possible cases like this. So, okay. So yeah, this is like trace of a potential in H. This is usually, as I said, the literature in random matrix theory usually addresses cases like this, single matrix and single trace. So let me then give you a little bit of thing about random matrix theory then. There are two almost exclusive classes of ensembles in random matrix theory. There is this so-called unitary invariant ensemble where the measure is a unitary invariant function like the ones that I was discussing. And there is another class, which is Wigner ensembles. So Wigner ensembles are IIDs. They have IID entries. It is a matrix, well, except for the symmetry, for example, to be Hermitian, the entries are independent, identically distributed random variables. For example, you can keep that in mind. And these two classes are almost disjoint, except that they meet in some nice intersection, which is Gaussian unitary ensembles. If you work with real matrices like symmetric matrices, this is Gaussian orthogonal ensemble, and there is also Gaussian symplectic ensemble, which deals with the other field, which is quaternion. So let's not discuss that. This whole thing is called the Dyson 3-4 way, and Dyson has some nice way of interpreting or justifying why these three fields are C and quaternions are relevant for quantum mechanics based on symmetries of the system, like time reversal symmetries and this thing. But the measure, importantly, is of this form. It's almost like a Gaussian measure. Of course, we are dealing with a space of n by n Hermitian matrices, which is a real vector space of dimension n squared. So the H is a usual Lebesgue measure on that space, and you just write it like this. And Z, of course, is the total integral to make sure that this is a probability measure. Okay. So the origins of this story, just one page, let me tell you, it all goes back in a way to Wigner, actually, and these Wigner ensembles. So Wigner was interested to understand the nature of spacing or distances between, so just understanding the energy levels, not quite the energy level, but differences between energy levels in neutron scattering experiments. So this is like original quantum mechanics problem, where you want to understand the nature of these spectral lines in terms of some theory, which turns out to be quantum mechanics. But this is much more complicated because they didn't have good theories about the nucleus of the atom. So what Wigner did or assumed is that, okay, we don't know anything about this black box. Let's assume that this is a random matrix. Entries are distributed according to some IID, and which we have no access to that IID. And let's assume that this matrix is finite, but then we just work with finite n and let n go to infinity, and see in the limit we can see some structure. We can maybe discover the structure of distribution of eigenvalues of this matrix or other finer quantities that he was after. So this was Wigner's original idea. But amazingly, actually, Wigner got the idea from reading a paper, or actually seeing a formula due to Wishart. Goes back to 1928. So Wishart was a very good statistician working for the Department of Agriculture in UK around that time. And he just hooked up these covariance matrices for finding the covariance or correlation between different sort of agricultural produce that's grown in some area, for example. And you want to know if there is a correlation between, the yield of wheat and barley and other things. But this can be applied to any sort of correlation problems. For example, in your class, you might wonder, or in university, you might wonder if there is a correlation between doing well in math, physics, being good in sports and stuff like that. So you always run into this sort of covariance matrices, and understanding the eigenvalue and eigenvectors of this covariance matrix is what principal component analysis do. They do all the time. It's a very important technique. So understanding at least the large n behavior of eigenvalues and eigenvectors of matrices like C is of practical importance. The final formula was found by Marchenko and Pasteur much longer after, in 1960s or maybe 70s, I believe, much longer after Wishart, but the impetus was from Wishart. So that's an interesting lesson. So even agriculture and statistics can teach us a lot of things.
So sorry, may I have a question?
Yes, please.
So regarding this work of Wigner, so
yes.
what he was able to obtain in this consideration? So he considers all possible Hermitian matrices of size n by n.
Yes.
And somehow he managed to produce some kind of, I don't know, distribution of the eigenvalues, and then
yes.
And then he takes n going to infinity, and what is the result? That it somehow converges?
I will tell you. It's coming. Yes. I will tell you. This is Wigner's semicircle law, which I will tell you. But Wigner was not really interested in distribution of eigenvalues. What is important is distribution of differences between eigenvalues, because that's what you measure. You don't measure, you never measure, eigenvalues in quantum mechanics. You measure the difference between the two. So this is called level spacing. And in this regard, he was not successful, but he had an amazing idea. He took just 2 by 2 real matrices, symmetric real matrices. The 2 eigenvalues are real, of course. Just look at the lambda1 minus lambda2 as a random variable and find the distribution function of that. This is a completely well-defined problem. And Wigner solved it and found, for example, in the case of Gaussian orthogonal ensemble, 2 by 2 matrices, by the way, this question for 3 by 3 is very hard. For 4 by 4, it gets really, really hard. And finding the limit even is very hard. This was solved, the final question was solved in I believe, 70s or 80s. This is a famous Tracy-Widom distribution, which was discovered much later. But Wigner had this amazing curve discovered. This is called Wigner's surmise, which is very close to the actually n by n and infinite by infinite limit situation. So this is an important thing to know. So as we were discussing, one interest, the simplest primary interest could be that finding eigenvalue distribution functions. So this function mu n is a probability distribution valued random variable. So you want to, you want to study this. This is a very discrete object. So if you average it, you get something, mean density function. You integrate this random variable mu n against the measure that you have on the space of n by n matrices. You get this function rho nx. This rho nx is a smooth function, but it's extremely hard to find this equation. It's possible in some cases, in the case of GUE, but it's very, very hard to find this equation. But in the limit, you can do something. So the limit is to find limit of this probability density functions rho n as n goes to infinity. Of course, I should say in practice, and that's very easy to see that what you really want to understand is tracial moments, limit of average value. By the way, in this talk, when I put these angular brackets around formulas, it means expectation values. So this is a random variable, 1 over n trace of ak over a space of n by n matrices, and you just take its expectation value or mean against the measure that you have, and this is a number, and you let n goes to infinity. So what Wigner discovered is something you can experiment with any program, maybe MATLAB. Okay, this I produce using MATLAB. Histogram, take 3000 by 3000 GUE. So n is equal to 3000 GUE matrix, and draw the histogram of its eigenvalues. You get a semicircle like this. Of course, there are fluctuations because this is a histogram, and it has to be. And the smooth formula is very complicated, but it all smoothly approximates this. But then as n goes to infinity, you get a very nice formula, which is called Wigner's semicircle law, which is this one, rho of x equal to 1 over 2 pi root 4 minus x squared. And this is the first case. This is the easiest case. So the unitary ensembles that is more general, you want to study, or as I said, the simplest, the case that mostly study in random matrix theory, they are like trace of V of H. And so you can use a Weyl integration formula to write this integration instead of, there's a huge symmetry in this integral. So you can just break the symmetry and write it as an integral over the eigenvalue space. So once you write it as an eigenvalue integral, you discover the joint probability density functions of eigenvalues, which is given by that. This comes from this Weyl integration formula, but it's just a reduction of integral using symmetry. And basically, it uses the kind of writing a Hermitian matrix. You can always write it, it's just based on the spectral theorem. You just write Hermitian matrix in the right orthonormal basis as diagonal. Those diagonals are eigenvalues, and this leads to this. So in the three fields cases, R, C, and quaternions, beta is 1, 2, 4, and so this leads to a model, to an understanding of these things, which is called Coulomb gas models. So you have to think of it as like a gas of eigenvalues. So lambda 1, lambda n's are particles moving on one line, on one dimensional line, and the interaction is controlled by terms like this. So the Vandermonde determinant here is is the difficult term, which signals the eigenvalue repulsion. So eigenvalues of Hermitian matrices don't like each other. I mean, the chances of you take a Hermitian matrix at random and eigenvalues are very close to it are negligible. And that's very strange in a way, because the entries of the matrix are independent except for symmetry, but the eigenvalues are not independent. And in the diagram I showed, I mean, if they were independent, they would satisfy Poisson curve, but they are not on Poisson. There is something which is on Wigner surmise curve. So that's something to take away. Another thing that we need is a formula which actually write a perturbative expansion of such integrals. This formula is originally due to Hooft. In 1970s, Hooft was interested in quantum chromodynamics. I mean, the group there is SU2 and SU3, so it's very hard to solve. So Hooft's idea was to let us work with SUN, let n go to infinity. Maybe you can solve the limit at infinite. We can solve the problem at infinite limit, and then perturb or expand near infinity. So then let n go down again to 3 or 4, something like that. So that was Hooft's strategy. So the formula that he found is called genus expansion or topological expansion or 1/n expansion. It goes by all 3 names. This was worked out in perfect, generality and very nicely by Brezin-Itzykson-Paris-Zuber. I should say Parisi, of course, you all know Hooft got Nobel Prize in physics several years ago, and Parisi just got Nobel Prize in physics this Monday. So that's, yeah. Anyhow, so what is the formula? The formula is that if you take log of this partition function, you can always write a 1/n expansion. So there's a leading term, which is n squared, but then the terms drop in n, it's 1/n. These FGs, the coefficients that appear, they can be written. I mean, these are like Feynman rules or Feynman diagrammatic method, but done for matrices. So you have two indices for matrices. These two leads you or led to Hooft and PIPZ team to work with surfaces instead of usual graphs. So this set is the set of isomorphism classes of Feynman-weighted, connected, closed maps of genus G. So I will say a little bit about this, but then we move. Okay, so now, so this was our first thing. So I had Shahab Azafar, my student. It was a lucky situation because Shahab that year went, as he was working on this problem, he went to he attended this school in US, this Princeton summer schools on random matrix theory that year was organized. And so he learned a lot of techniques there. So, and the relevant things, especially what he learned was this topological recursion, because we immediately saw that the methods that usually you learn in random matrix theory are not applicable to our problems. But we thought that, okay, let's use topological recursion. Maybe that would be the method. And so that was the original thinking. This topological recursion was pioneered by Eynard-Orantin and other mathematical physicists, I believe, in the Russian school. So it relates to a lot of beautiful things, but originally, really, I should say it comes from Mirzakhani's recursion when she found a recursive formula to compute the volumes of modular spaces of Riemann surfaces. So the Mirzakhani recursion is a very special case now of this general scheme of topological recursion, which covers many things, not just random matrices. So this is from this paper with Shahab. So let me tell you a little bit about just what recursion is. The goal is to find some meromorphic symmetric n-forms. So if you find these sort of symmetric n-forms, so I mean, yeah, the idea of symmetric n-forms sounds like oxymoron, right? Because I mean, forms are supposed to be antisymmetric. So these are really forms on n, Cartesian product of the surface, with itself. This surface is called a spectral curve and naturally emerges from theory. So these are holomorphic sections of some line bundles, are actually symmetric tensor product, exterior symmetric tensor products of canonical line bundles of these Riemann surfaces. That's the technically what it is. And recursion is on the negative of the Euler characteristic. So because Euler characteristic is negative, its negative is positive. So you can do recursion on the negative. Then if you can find a formula for all omega GNs below some limit, then you find omega, you find the recursion, you find the formula that you want, omega GN, by using recursion. And basically what this picture, which is due to Eynard, says is that all the way you can excise a pair of pants from a surface with boundary, and you can glue them by another surface, all the possible ways gives you this decomposition. And the formula involves some kernels, some pieces of Riemann surface theory, even theta functions in some pictures can emerge, but okay, but that's, in the paper with Shahab, we did, the first two forms are omega 01 and omega 02, which are, in a way, these are the most important things to calculate. Once you calculate them and you have patience and energy, you can go on and calculate the whole kind of forms omega GNs. And once you have omega GNs, these correlations and objects of interest, like or expectation values that you want to compute, they come from computing residues of these meromorphic differential forms, or higher residues of this meromorphic differential. So that was the method that we tried to use. And but one thing about this method is that this is formal. I mean, the perturbative expansion is formal, but the work that was done was not for formal matrix integrals. It was for really convergent, those things that John Barrett and Glaser wrote, that they are convergent matrix integrals, and we want to get something. I mean, one of the things they discovered was there was a phase transition, and discovering phase transition using this method, so it takes some, it's not clear. So we decided to work with non-perturbative methods, so to speak. So one technique is to use Stieltjes transform. So this is a very general idea, or Cauchy transform. It depends what it goes by all different names. So when you have a matrix H, you can define a function on the upper half plane by taking trace of 1 over z minus h. Of course, this is resolvent of the matrix. And this function is holomorphic in the upper half plane. If your matrix is, we are assuming the matrix is Hermitian. So eigenvalues are on the real line. So above and below the line, this is a holomorphic function. If your matrix is not deterministic, is probabilistic, you can take its average value, which is given by that integral, against the measure that controls the distribution of eigenvalues, and then you get a holomorphic function in the upper half plane. So the holomorphic function has an expansion near infinity for z large enough, which is given here. So this is a very important thing, and if you can compute this for your problem, you can go back and compute the probability, the distribution function, density function of eigenvalues by just approaching the real axis from above, taking the limit of imaginary part. This I is imaginary part of this GN. For finite n, if you can find this for finite n, even works. But usually you don't do it. You cannot do it for finite n. But for infinite n, some nice patterns emerge. Because for finite n, you can write down an equation like this for the green function. By the way, this is also called green function of the theory because it's resolvent, and resolvent, of course, is green function, more or less. So it satisfies an equation like this. But as n goes to infinity, you can safely drop this 1 over n, and then you get an algebraic equation for your green function in terms of some quantities that are, some of them are obviously known, like V is a potential, right? So you get this potential, you take derivative, and there is this function P of x. So P of x can also be computed in terms of the data, in terms of the information that's in V of x, but it's a bit more complicated in a way, but it's doable. So in general, what you get, well, I mean, what happens is that the solution, the spectral density is of this form. So this is a product of x minus ak, x minus bk. So you have to imagine the, you know, in the case of simplest case, V of x 1/2 x squared, we had these semicircles, Wigner semicircle. But then if for general potentials, you don't have semicircle, you have much more complicated curve, but it's still like with finite support. And then another interval, another curve with finite support. So this is really what it is. It's really an algebraic curve. Actually, it's an hyperelliptic curve. You're looking only at its real values, so on the real line. But what this topological recursion and better random matrix theory techniques suggest is to use this thing now is this hyperelliptic curve as a Riemann surface and work directly with that. And that's a spectral curve, and that's a very, very important kind of brings a lot of interesting techniques from Riemann surface theory or other areas. So the problem that we tackled, the simplest problem we tackled was involved a potential f of h, which is, if you write it in terms of eigenvalues, it's of this form. So there is an integration over Rn, which is the eigenvalue integration. There is one extra term, which is u of lambda I lambda j, and this v is the potential, which is dictated by the spectral triple. So this piece is completely dictated by the spectral triple. You know, it was like trace of d2, well, g trace of d2 plus trace of d4. That gives you this v term, but this is a new term. This is the new term. Okay, so you have to now analyze this this partition function. If you see, you can evaluate it or not. But the method that you have to use in this case in order to find rho of x, the spectral density, is a method that's, again, it's like a variational principle, but this equilibrium measure of variational principles is exactly the Borel probability measure that minimizes the energy functional. So if for each probability measure, you define a functional, which is completely controlled by your potential. So this is the new term U of ST, but the V potential and this log term they are present in all problems. This is the new one that depends on your model. Of course, V also depends on the model. So these things, using variational principles is kind of risky, but in this case, actually, Percy Dave really has done the hard job and has proved a lot of delicate, precise mathematical results that shows that this method works and is precise. He has a huge theory, nonlinear Riemann-Hilbert correspondence that applies to random matrix theory in many general cases, but we didn't need that. Just so the thing is, this rho, this function rho, satisfies an integral equation, which is here. So the integral equation gives you, it reads a PV is principal value. This is kind of Cauchy principal value of this integral. You could have singularities on the line if you cross the spectrum. And you just have to find M1, M2, and M3. So this is the paper that I did with Nathan. So we looked at this, we computed this rho x spectral density function. It's a function of coupling constant. For each G, you have a coupling constant. But when you draw that, you notice that something interesting happens because this curve, which had only one cut, like start from the exterior, you have, from the interior, like look at the red curve, for example, and look at the blue curve. As the values of G changes, you cross a threshold. You cross a threshold, and after the threshold, you have two cuts. After that threshold, you have two cuts. So this threshold can be computed explicitly, GC, and turned out it's exactly the value that Monte Carlo Markov chain showed in Barrett Glaser paper. So this was very good. So this was one of the first goals that we could find, hopefully, analytic proof of existence of phase transition, and maybe computing the point that phase transition happens in the model. Of course, the model, I mean, we treated is the simplest possible model of these spectral triples. If you take a little more general spectral triples, it's just far more complicated, I should say. So this is the this was in this paper with Nathan. Then we tried to, with Nathan, we tried to study spectral statistics of Dirac ensembles per se. So you see, you have two issues here, right? We have two problems here. One is the spectral statistics of H, the Hermitian matrix that defines your Dirac operator. The other one is a statistics of the Dirac operator itself. So these are two things that are different. So this paper is newly posted. One of the results that's shown there is that the spectral density of Dirac operator for non-commutative geometries of all kinds, well, these are finite, real, simple, non-commutative geometries. And as you all know, the classification of these spectral triples, they are parameterized by two numbers, P and Q, and P plus Q is called signature. So, but for all signatures, if you use Gaussian potential, the spectral density of Dirac operator is the convolution of the Wigner semicircle law with itself. So I found this result, I mean, quite appealing, in fact, because it's very general result. It's a very, very general result for all geometries. If you use Gaussian potential, you get the convolution of the Wigner semicircle law with itself. This red curve is the Wigner semicircle law, and its convolution with itself is the blue curve. It's a blue curve like that. So to prove this, we had to use those techniques of topological expansion, work in some detail, prove existence of topological expansion, and start from there. So beyond the Gaussian, if you use more general potentials for some geometries of signature lower than, I think maybe 2, I think, total signature lower than 2. I think still you see this pattern, but in general, we don't know what's going on, if the convolution law still holds or not. I think that's an interesting question. So,
may I ask a question?
Yes, please.
So in the previous slide, yes, this sentence, regardless of geometry, refers precisely to this fact that independently from the signature, you will get the same result, yes?
Yes, exactly. Because you have the signature PQ. I mean, the signature defines for you the fermion space. I mean, you know, like in classification of finite spectral triples. Basically,
yes, but the general assumption is that the Hilbert space is always MN matrices.
Yes, that's right. Yeah, because these are simple spectral triples. So the Hilbert space is MN. Simple real spectral is always MN.
Okay,
so
okay. Simple means that the algebra itself is simple.
Algebraic sense, yes, in algebraic sense. So if you want, in a way, we are working over a non-commutative point. Over just one non-commutative point. I mean, So, okay, so what happens to 2 points? Okay, so this another thing. Okay, so yes, this is the one. But as I said, now this ideas that we used in previous 2 papers, really, or 3 papers, I should say, so far I discussed, really deal with very special case because they deal with one matrix models. I mean, in some cases they are multitraces, which is general, and that kind of forces you to look at more modern techniques. But they were always one matrix model. But if you allow your signature to go to 2, you immediately have to deal with 2 matrix models. And maybe 2 trace or multi-trace, 2 matrix models and multi-matrix models. So this is where all the complications exist, because I mean, techniques are very, very rare, and these models are not very integrable. I mean, any case that you prove these models are solvable or integrable, there is some special, very, very special, I would say, algebraic things in the potential that allows you to do that. I mean, in general, it's very difficult. So this question, nevertheless, there is a way to handle these things, not completely analytically, but with precision, with good precision. This is the bootstrap. So I'm coming to the title now, after all, which is the last paper. Well, yes, not quite last, but yeah, one of the last papers we posted with Hamed Hessam and Nathan Pagliaroli. So we saw a paper by Henry Lean. I think he was in Princeton when he wrote that paper, which looked very promising and had a totally new idea. So this was the idea of using bootstrapping. So, and then it turned out that actually the paper, the technique that was used by Henry Lean, there was some form of it in a previous paper, recent previous paper by Anderson and Krushansky. So this is, of course, I mean, we use Schwinger-Dyson equations, you know, in the topological recursion paper and more than that. But the way that Schwinger-Dyson equations, as I will discuss now, is used, it's very, I would say, it's quite analytic in a way and very precise and gives you results. So let me get into that slowly now. By the way, the word bootstrapping is used in different ways in physics. There is this conformal bootstrap, and there is also S-matrix bootstrap that they use in quantum field theory. It always means you put some constraint on your unknowns, and these constraints gives you more restrictions to possible solutions. And once you have more restrictions, you can just try to maybe just give you less choices and more freedom. So I mean, well, less choices, not more freedom, really. More freedom to get better results, I would say. Anyhow,
but then the idea is that you get everything that satisfies these constraints, right?
Yes, I mean, the constraints are strong enough so that okay, so there is something there, though. I mean, I should not quite say yes, because the constraints depend on the cutoff. So once you fix the cutoff, they give you good results. But once you increase the cutoff, they give you better and better results. And so let me now give you the general idea. Did I answer your question, Piotr? I mean,
well, it was more of a comment. I mean, I'm used to this bootstrapping, like in the context of UCT, right? Universality theorem, right? That the idea is, yes, you put constraints, so it must be generated from something. It must have some properties, but then you take everything, and sometimes you don't know really what you get.
Oh, I see. Yeah. By the way, Claude Choquette, who invented, also coined bootstrapping in UCT, wrote to me yesterday after he saw the announcement and said that, by the way, is that related to, to my bootstrapping? I said, well, we don't know, but maybe there is, because there is some logic, there is some internal meaning in words. Maybe down there they are connected, who knows? I mean, but nothing that I could say right away. I mean, would be wonderful to relate KK theory with random matrix theory. I mean, that would be another big thing, I think. Okay, so anyhow, so bootstrapping is done in 4 steps. First, you have to find the Schwinger-Dyson equations of the model, and then you go to large and limit to find the loop equations, and then find the dimension of the search space. I will define this term. Basically, it gives you the number of sort of free variables in Schwinger-Dyson or loop equations. So then you apply this result, which is actually the easy side of the result. I mean, the result is very general, but I mean, we just use the easy side of the theorem, Hamburger moment theorem, which is positivity constraints. And you have to choose a cutoff. You have to choose a cutoff to find words with length. Well, I'll tell you what this means, but really this cutoff is very, very important because to do this, to do the calculations. So now, as I said, that the general thing you're struggling against is basically a multitrace multimatrix model, which is its partition function is given like that. So Hn to the power m, space of Hermitian matrices times Hermitian Cartesian product of Hermitian matrices, and you're using Lebesgue measure on the Cartesian product. But then this S, the potential, is a very general function on in these non-commutative variables H1, H2, H1. So the Schwinger-Dyson equations relate moments of the model in these non-commuting matrix variables H1, H2, Hm, which you define as expectation values. So again, there is this expectation value 1 over n trace of W. So take W, for example, any word in H1, H2, Hm, any non-commutative word, and then you have a random variable on your big space, and then you take its average, so you have this this quantity. Now the beautiful thing is that these quantities for all layers of words, they satisfy some equations. That there are some algebraic relations between them, which, for example, in the case of one matrix models is like this. So it's some k from 0 to L minus 1. You see, the thing is, it reduces a 2x2 products of expectation values of 2 traces to expectation value of trace of basically one matrix. I mean, so this is S prime is the derivative of the potential. So if you want to go from 2 to 1, this is something. I mean, of course, the price you're paying is that you're now dealing with something which is of degree higher. And it's not clear that there is a recursive pattern in these things. And in general, there is no recursive pattern in Schwinger-Dyson equations. And that's the difficulty, actually. And that's what one of the problems that topological recursion really solved was to bypass that by introducing recursion, topological recursion. So, but important piece of thing is that there is a factorization in large n limits for these things. I mean, this has to be proved in each case. For example, in this case, the factorization can be proved using this sort of estimates. The product of expectation value of product of traces and products of expectation value of traces are related by O(n minus 2 term. So as n goes to infinity, yeah, expectation value of product is product of expectation values. So these MKs are these limit moments that gives you. So then these difficult equations gives rise to kind of simpler equations because of this expectation, because of this factorization property that are called loop equations. I mean, you can call them loop equations. And what is search space? Search space is really So this is a computer science term, I guess, or maybe optimization, or yeah, this is a calculation term. Is the space of lowest maybe dimension in your moments or your unknowns that generates all higher. And so the specific things that was discovered is that in these models we treated the dimension of search space as 1. So this is pretty good. I mean, so let me just explain that. So I will describe 2 results. One is type 1-0 Dirac ensemble that, of course, I mean, we wanted to do this just to test our understanding of the techniques and the robustness of methods, so that make sure that, you know, what we get is really kind of conforms with what we already knew by analytic methods. So this case 1-0, I mean, more or less we knew everything about it by exactly solving it before, but we tried to apply Bootstrap to this. So couple of results. I should say, I mean, Carlos Sanchez also has studied these things. When he studied this when he was in Münster, now he's in Heidelberg. So he has done work analyzing terms like this, and he has related this to free probability theory. So, I mean, free probability theory also has a lot to say about the subject. That's what Carlos is pursuing also. So he has some beautiful work on that. So this is, of course, I should say now, Reimer also pursuing topological recursion, but applied to his non-commutative field theory models, which you get very intricate special functions, and yeah, he treats the Kontsevich model in his own way, non-commutative way, and there are a lot of implications of topological recursions that he also brings to this. So yeah, I mean, that was the original goal from beginning, to, you know, to have different you know, kind of yeah, treatments of these models. So the loop equations in this case, you can just write it down, and the loop equations, if you notice that the odd moments are 0 because these are you know, even potentials, then you notice that the loop equations are simplified to equations like this down the page. So you have to compute all even moments, but then what turns out is that actually the second moment, the value of the second moment, and G will give you all higher moments. Now, recall the potential in this case, if you write that term, G trace of D2 plus trace of D4, expand in terms of H, you get a term like this. So you have, so then we do SDE, Schwinger-Dyson equations is what we had here. And dimension of the search space turned out to be 1. So now what we have to do is to use this hamburger moment problem. I mean, this is the easy side. The question is, if you have a sequence of moments of real numbers, when this sequence are actually moments of some probability distribution or just a distribution function, when such a thing is possible. Well, I mean, one direction you can easily show that. We can easily show that this is, if this is the case, then this Hankel matrix of the Hankel matrix of moments has to be a positive definite, not positive definite, positive semi-definite matrix. So the Hankel matrix is just, yeah, you form it like that. It's a symmetric matrix. So being positive means that all principal, minor matrices like 2 by 2, 3 by 3, 4 by 4, they have to be positive definite. I believe this is necessary and sufficient condition for positivity of the big matrix. So, okay, so if you apply these things to your problem, to the moment problem, and if you write everything in terms of, well, M0 is 1, of course, we know, and M1 and M3 are 0, so this you can drop them. And if you write everything in terms of M2, you get infinite system of inequalities, right? You get infinite system of inequalities. But what is special about these spectral triples, models that come from spectral triples, is that there is, as I said, there is also this Dirac statistics, and there is this positivity of the Dirac Hankel matrix. That's another set of constraints, their positivity. So the distribution, I mean, these Dirac limiting moments are defined like that, and all these things exist, and these are just finite numbers. And this Dirac matrix, big matrix of Dirac moments, have to be also non-negative. So this is the extra thing. So this was then, so the result was a lot of very, oh, this is not coming very nicely here. Oh, it takes time, it takes time. This file, yeah, it still is not okay. Now it's loaded. Okay, it took some time. Yeah, it's a. So this was done really by Hamed and Nathan. I mean, this is quite. It was quite a difficult calculation. Computer simulations. I mean, not simulations, calculations. To write down. So we took lambda, the cutoff, to be equal to 10. Actually, the cutoff was 10. And then you have two parameters to play with, right? You have M2 and you have G. And for each G, we know that there exists a unique M2, of course, because the model, defines M2. But the question is, where is M2, the second moment? Well, the second moment for each value of G really lies between, on the intersection of all constraints. So if you take larger and larger matrices, eventually you narrow to this blue line, and that's where the M2 is. And so this is for values of G between -5 to -2.5. That's first case. And then you study for values of G. You cross 0 and then you reach to value 1. But what you notice is that at the threshold, which is here near this point, the behavior, the dependence of M2 on G changes. Here is a nonlinear dependence, but here there was more or less a linear dependence. And this is exactly at the phase transition points. So, I mean, I don't know the theoretical understanding of this. I don't know if there is a theoretical understanding why this is, but this is something that's observed. So that's okay. So, and then it conforms to what we calculated analytically before. So this was pretty good. But the main thing was, so this is the thing. But the main thing was really to study type 2 geometries, which would involve two matrices. So let me go to that. Okay, at least now let me define one spectral triple, maybe carefully for you. So this is type 2-0 random geometries. D, the Dirac is, you take these gamma matrices, gamma 1, gamma 2, or well, in this case, Pauli spin matrices really. And you have two operators that defines your Dirac. Dirac operator A and B are Hermitian matrices, and you're taking anti-commutators with A and B over there. So the partition function, again, we took the partition function to be quartic. I don't think, I mean, of course, quartic is really already very, very complicated, but I mean, going to degree 6 or higher degree potentials, I'm not sure what's going to happen. So in this case, because you have two operators, I mean, two matrices A and B, integration is over space of matrices time Hermitian times Hermitian, of course, but then the terms are much more complicated. So these are the terms that you can study. You have to study. I mean, they appear in your partition function, these terms. Okay. Okay, so then the partition function, as I said, can be written in terms of random Hermitian n by n matrix variables A and B, and the partition function is of this form. This is DAD. So this is now a two matrix and multitrace matrix integral, and this is more or less frontiers of random matrix theory techniques. I mean, that's what this Lin paper was about. I mean, of course, I mean, his potential is still much more simpler than the potential that we have here. Potential is much simpler than this potential, and that's what you know, you want to understand what's going on. And this bootstrap, in this case also, so we decided to apply. So the thing now you have to do, you look at you have many more moments than just traces, because you have a non-commutative polynomial in two variables A and B, and then yeah, you label them like M, A, B, C, D, for example, and then higher labelings, of course, are needed. So the whole hierarchy of moments is a huge set that's parameterized by all these A, B, C, D, E, F, so on words. So any word in non-commutative variables gives you a moment. In the large n limits, then these Schwinger-Dyson equations, you have to work it out, gives you loop equations like this. Again, you see, these loop equations are hard to analyze because, I mean, these are not linear recursions. They are quadratic recursions. And the structure of terms are complicated. They are not, you see, I mean, for example, look at this term, ML111. L111. So this is a term of, you know, total degree L plus 3, and this is total degree L plus 3. But here this yeah, the products of degrees seems to be, the sum of degrees seems to be matching, but the structure, I mean, how to organize these things is not very, very clear at first. So then we had to analyze this thing. So the question is, what is the dimension of the search space? What it can be shown after proving some combinatorial lemmas and propositions that dimension of search space for this model is also 1. So basically, it means that you can really solve and constraint all higher moments in terms of the coupling constant of the problem G and the second moment. So this was very good news. I mean, so higher moments then can be computed by solving some linear equations in that case. So again, I should say this is also a piece that does not exist in other literature. I mean, when they used loop equations, they never solved, you know, for moments below cutoff. They used these solvers, so they just directly work with constraints. And I still don't know how you can get constraints to constrain enough for you so that you can get precise information. Because in our case, all these higher moments up to some cutoff level are computed in terms of M2. And then you put it into this Hamburger matrix, I mean this, sorry, Hankel matrix, positivity of that, you just write 2 by 2, 4 by 4, 6 by 6, and so on. Positivity constraint, you get systems of inequalities. You can draw it in G and M2 using computer, of course. And then you have to see if this is converging somewhere or not. And this is what happened. So, so the structure of these terms is very interesting. I mean, it would be, I believe there is a general pattern. There is a formula to these terms because look, I mean, these numbers are all rational, but the meanings of these numbers we still don't know. But this was used up to, because the cutoff was 10, so to compute the constraints.
Sorry, could we go back to the previous slide?
Yes, yes.
In the formula for M8, you have the constant
M8,
term, is it correct? 3 over 400.
Sorry?
Shouldn't be there some coupling constant here? Yes, exactly.
Oh, this one.
In every other terms you have previous
yeah,
moment or coupling constant.
Yes, there should be something is missing here. It's
Something is missing. Okay.
Could be M0. Let me ask Hamid, is something missing here? Maybe Hamid can answer.
I think it's true, but I'm not completely sure about that.
Nathan?
I think there is a constant in some of them.
Is it M0?
Yeah, I think Hamid's right. That some of them might have a constant.
Oh.
So it could very well be true and not be a typo, but I can't say with absolute certainty without checking our code again.
Okay, well, that's a very good point. Yeah.
Okay, thank you.
Yeah. Okay, very good. So yes, so the Dirac constraints also starts by writing D2, D4, D6 in terms of G and M2, and then you're using Dirac constraints separately to do the things. Now, there is this, of course, non-commutative moment problem. And well, in this case, again, we use the easy direction. I mean, if you have like moments of some multimatrix, multitrace partition function, like there's a word W in random in variables H1, H2, Hm, and trace of this integrated against those words. If you form a something similar to Hankel matrix, which is by juxtaposition of words, you get a matrix which is non-negative again. You can prove this easily again. But the inverse problem, I mean, what kind of conditions is needed in order for this to be moments of such thing? I'm not sure. I think there is some work, but I don't think there is a definitive answer yet. But that's a different question anyhow. So we have this. Once you put this, so for example, let's look at for example, this matrix of moments, MA, MB, MAA, and so this matrix has to be positive or non-negative matrix. So all sub-matrices also have to be non-negative. So that's these are kind of constraints that you have to deal with in your computer, and yeah, there is a lot of codings going on. This is coming up with this picture was not easy at all. So again, for this 2-0 quartic model, the search space, of course, as I said, is one-dimensional, but then there is a beautiful convergence into this velvet line or maybe blue line. So this line, and so this gives good values of M2 of the and then you have those recursion relations. You can find higher values step by step. And basically, so this gives you a way of solving these models. I mean, there is it is not fully analytic because it also depends on this computer work. And but it's not totally like Monte Carlo simulation either. I mean, it uses the theory. Of course, I mean, one issue here is what if you take a bigger cutoff, and then you have again a huge another huge matrix or matrices to write down constraints, and who guarantees that as you take bigger and bigger cutoff, these things actually converge, give you the same thing? I don't think there is a theorem yet, but hopefully there will be a theorem. I mean, to show that actually under increasing cutoffs, the things, values of M2 that you find actually converge. I mean, there is, because I mean, computer experiments shows that they converge, but you need a proof. And this is for values for a smaller than -3, where again the dependence is linear between G and M2. So this is also a phase transition for that geometry for this quartic potential. in that case. So this is okay. I think that's so. Let me just give you a summary and outlook of this. As I said, the relation between M2 and G appears to be linear for values of G roughly below the phase transition. So we speculate that the Dirac eigenvalue density function after the phase transition is of a similar form to the random matrix eigenvalue distribution of the type 1,0 for G less than the critical value of G. It's less than that value GC. So now just looking at Bootstrap and these loop equations, so this is a kind of alternative, attractive alternative to study Dirac ensembles and random matrix ensembles. I mean, Monte Carlo simulation is also powerful, but the size of matrices cannot grow too much. I mean, there are issues there. I mean, especially with multimatrix model simulations. And another issue is that, of course, these models are essentially non-integrable, really. And so fully analytic methods to analyze them, where they will come from, I don't know, we don't know. But these models are basically non-integrable by nature. I mean, unless your potential is very special. I should say that coming from spectral triples has some features that is completely lost on random matrix theory, people, because when you untangle the things and you write everything in terms of H, you get kind of unwieldy expression in terms of your Hermitian matrices. But let us not forget that they came from very natural things originally in terms of Dirac operators. So that's the hope. That's the hope that one can prove actually general conjectures, general things about this sort of multimatrix, multitrace random matrix models, as opposed to very general models that in very general models, they really take quartic potentials and these things, but of very special type. And then when you have H1 and H2, and then, yeah, I mean, also of very, very special restricted types, because the problem is just so hard. I think I'm done, Piotr. Thank you very much.
Okay, thank you so much.
Thank you.
Let's clap hands virtually. Okay, we've got it. So we still have plenty of time for questions. So fire at will. Who would like to ask MASOUD some further questions? Adam, are you happy?
Oh, there is Shahab who has a question.
Yeah, so go ahead.
You should answer the question, Shahab, not.
So I think I missed part of your explanation in about the last paper.
Yeah.
So do you hear me?
Yes.
Yeah, I can hear you, but not very well.
Is that fine now? No.
Well, I mean, the level of sound is fine, but it's extremely distorted.
Oh, fine.
Now I can hear you now. Let's try.
Yeah, but go ahead.
Okay, sorry. Sorry. So my question is about this diagrams actually. That I mean, when they wanted to become loaded, it took some time. So we have three parts there: the yellow part, the blue part, and then there was this. And you were using, I mean, you were mentioning about convergence of, I mean, first of all, I don't know the meaning of these three parts.
Okay.
Where do they correspond to? Mm-hmm. And then what do we mean by convergence? Convergence in terms, I mean, do we let n go to infinity and calculating something?
Oh.
Is that?
No. N, no, the thing is, in these things, n already has gone to infinity because we use loop equations where the factorization is used. I mean, factorization of those tracial moments is used. So n is already at infinity in these things. What is what is important is to notice that, you know, when I define this expectation value, you know, I said, you know, moments, right? So, and then we have these positivity constraints. Okay, so you have infinite number of positivity constraints. And so you want to take moments only up to length 10, for example. And then you have finite number of positivity constraints, because you cannot implement infinite positivity constraints on computer, as you know, right? So what one has to do, you have to, this is the cutoff lambda. It's really a cutoff, I mean. And then once you fix that lambda, you have finite number of positivity constraints, and those regions correspond to different positivity constraints. And now what you have to see is the following. Just look at the vertical line. So you see that the x-axis was G, and the vertical axis is M2. Look at the vertical line, and when you go, there is a window. That's the only possible values, I mean, only possibility for M2 as a function of G, because M2 is a function of G. M2 is a function of G, because the problem defines its moments uniquely. So M2 is a function of G, so there is only, and then this thing narrows and narrows. But now here is but then the convergence problem is the following. You have this issue that you have chosen a cutoff. You bring in more equations now. So, okay, I mean, who guarantees that you're going to get the same sort of, I mean, but I mean, experimentally, that's what I think Hamed and Nathan have seen this by experimenting. But I think one has to think about this question and provides a proof. I think there's. By the way, I think it's an interesting question that also Lin and I mean there is a paper by Kazakov on this now, and there is also another group in Stanford who are doing matrix quantum mechanics. They used this bootstrap. They also have this question. I mean, they also haven't settled this question. So, I mean, this is a kind of interesting analytic question to think about. So, that's what I can say.
Okay, thank you. Thank you.
Okay, yeah. Thanks.
Okay, Adam now.
Yes, still I have some question. One question is in fact some sort of a philosophical question. So, what is the correct way of thinking about letting n to infinity? One should think about this that somehow we approximate our space with some
well, I mean, so let me go back to the case of Wigner, for example. I mean, like with this Wigner work. I mean, n goes to infinity because you are really cutting Hilbert space to you know, to n-dimensional pieces, and you take larger and larger pieces inside your Hilbert space. Because of course, I mean, the Hilbert space of quantum mechanics is infinite dimensional, right? So choose a good, you know, eigenvector basis, orthonormal basis, and you cut down the Hilbert space to this, smaller and smaller pieces, and then let n go to infinity. The analysis is much simpler if you start with finite.
Of course, but
yeah.
physically one thinks of this procedure at looking on the space up to some, I don't know, energy level or something like this. How to think about it physically?
Yeah, oh, physically also. Yeah, I believe physically also, because if the if sorry, if your Hilbert space, the subspaces are controlled by eigenvectors of your energy, for example, energy operator, then these are really you're fixing energy to certain limit. And then you increase the energy and you go on. So this is like the idea of cutoff also in quantum field theory or renormalization. So that's what, yeah, that's what.
This is ultraviolet cutoff, yes?
Yes. Well, I mean, ultraviolet can have, I believe, can have different meanings, but in this case, it's really an energy, for example, is reasonable. In the case of Hooft for QCD, you know, I mean, his idea was even much more, in a way, very attractive. I mean, he said that, okay, I cannot solve the problem. The QC is very difficult. It's not integrable for SU3 group. You know, the group is SU3, right? For gluons and quarks and all that, right? So he said, okay, I write a theory for SUN and let n go to infinity. So you get larger and larger symmetry groups, and hopefully you can solve the theory at infinity, and then you expand near infinity, come back down to say something about n equal to 3, something like that. So this was to Hooft's philosophy. So you see, in this case, n it plays a different role for Hooft. Yeah.
Okay, and still I'm also a little bit concerned about the choice of the action, since you choose the action to be a trace of d to the power 4 plus some coupling constant trace of d squared.
Yes.
And okay, this is of course fine in finite dimensional, but somehow if we would like to imagine that we are no longer in finite dimensional situation, then d is not a trace class operator. One should rather consider something like the inverse to get something which is a trace class. So I'm wondering whether in this process of taking n bigger and bigger, maybe one would like to somehow change the action.
Yes. That's absolutely true. I mean, that's absolutely true. That's a very, very nice comment. So let me tell you what happens. That's another amazing thing about these, about the actions that come from spectral triples. You see, you don't see anything, any dependence on n. You don't see any dependence on n over there. It's like g trace of d2 plus trace of d4, right? Mm-hmm. So you have that. But if you write it in terms of h, if you write it in terms of your Hermitian matrix, n will appear in a very natural way. And actually, n appears in the right way for all coefficients. Okay, so let me tell you. Let me take your question from beginning again. Yes, you're right. I mean, this question is the limits always have to be rescaled. You know, I mean, it's always rescaled limits, like in probability theory. You know, like central limit theorem. I mean, of course, you cannot say the sum of independent eigenvalues is converging to. You have to scale by root n. It's always a rescaled limit you take, right? So in this case also, you have to rescale eigenvalues. If you don't put n, so for example, look at GUE. If you don't put n, you just have e to the minus 1/2 trace of like h squared. If you do that, then you have to rescale eigenvalues by 1/√n, and then you have a right limit at infinity. Otherwise, you don't have a limit at. So this rescaling is a very, very delicate, very deep issue, and needs a lot of understanding. In all kinds of problems, you have to choose the scaling in the right way. But what is very interesting is that in this case, for spectral actions coming from, not a spectral action, sorry, no. I mean, for these actions that we use coming from spectral triples, you don't put an n, but when you write in terms of h or h1, h2, and whatever, even in the multitrace case, the coefficients that we needed already takes care of scaling in a very delicate way, actually. Mm-hmm. So this is something that I still don't understand. I mean, so I have to talk to John and Lisa and maybe my students also. So what is so? This was mentioned to me by Nathan, by the way, that because I was worried that, you know, we have to, of course, Shahab knows this very well. I mean, from his experience, I mean, you have to, you know, fine tune the way that n appears in front of everything. If you are working with general potentials from multimatrix models, but if you start with spectral triples, coefficients of n is exactly chosen for you in the right way. For example, n cubed, n2, n, this sort of things appear in the right way, and then so this is very good. This is very. This was a very good comment. Yeah, thank you.
Okay, thank you.
Anybody else? Any further questions or comments?
There is something in the chat, by the way.
In the chat. Thanks, MASOUD. Nice talk.
Oh, thank you, Carlos. Thank you so much. Maybe, Carlos, you want to say something about this observation about n? Maybe Carlos left, yeah.
No, he's here. He's just unmuted himself. Carlos, are you there?
Yeah.
No, okay. He
Because Carlos, you know, we always thought that free probability theory should have something. You know, Shahab remembers. You know, we were talking. I always says, yeah, we have to also use free probability. But that's what Carlos did. So that's very nice. Eventually, I think.
he muted himself back, so he might have some
Okay.
technical problems.
Might have.
Yeah, sorry, Mike is noisy. Yeah.
Okay. Yeah, Mike is.
So he cannot speak to us. Tomek,
Okay.
any
We
questions?
can talk later. Yeah.
Yes, I have a question.
Oh, Thomas. Yes.
Yeah, my question is this: how different is the random model, or possibly this phase transitions, from the classical critical model for the action functional? And what is the relation at all? Is there any relation at all?
Yeah. There is relation. In fact, if you look at the Landau-Ginzburg theory for phase transitions, they have a quartic action. I mean, this was the amazing achievement of Landau-Ginzburg. I mean, instead of looking at Ising model, you know, sort of discrete model, your variables would be spins. You know, you have this lattice, discrete lattice, you put on sides, spin up and down, and you try to understand phase transition using that by looking at partition function and by looking at free energy and singularities of free energy and all these things. Landau-Ginzburg introduced this potential, which is essentially just like, you know, it's like phi squared plus g plus some coupling lambda phi 4. And you integrate over a space of all fields. You do a path integral, a Euclidean path integral over a space of all fields. They were very, very successful with their model. Now, in this case, also this quartic is very nice. But of course, I mean, it's not the fields here are really random matrices. They are not like fields from classical field theory that you are quantizing in Landau-Ginzburg theory. Now, in terms of the idea of phase transitions, I should say, we took, I mean, also in the original thing, the term phase transition here, I'm not sure it's exactly like phase transition in, you know, in water to ice or water to vapor or magnetization phase transitions. It means that qualitatively the behavior of the system changes. Qualitative change, because I mean, you see the spectral density function, it goes from 1 cut to 2 cut. I mean, this happens when you cross the threshold. This you just understand as phase transition. If it is related to
The classical critical.
Classical critical value, I mean, critical phase transitions and stuff, I'm not sure. I mean, as I said, the only thing I can see, there is this Landau-Ginzburg potential, which is just shared between the two. I think one should understand phase transitions in a very general, in very, very broad sense. Yeah.
But even in the classical case, the notion of phase transition somehow has to do with the existence of how many equilibrium states, how many equilibrium measures are there. So if you are getting something like there is unique density, and somehow if we change our parameter, this is no longer true. You get
right.
models. This is in fact some kind of phase transition.
Yes, I mean, indeed, Adam, you're referring to this symmetry breaking mechanism for
yes. For example,
exactly. It was another idea also due to more or less, I mean, Ginzburg. I mean, sorry, Landau and Ginzburg. It goes back to them, even older, perhaps. I think so. But okay, I mean, there are all kinds of different phase transitions, you know, in statistical mechanics, and also even in thermodynamics, you have phase transition of order 1, order 2. So what you do, you just look at, you compute, for example, in the case of Ising model, you compute the free energy, log of the free energy, then you let the lattice size go to infinity, because this you have to do. Otherwise, you don't see any phase transition if the lattice size is not infinite. You go to some sort of thermodynamic limit, and then what happens is that, okay, then for certain values of your parameter, this log of the partition function properly scaled at infinity, computed after proper scaling, that's important. It shows, for example, a jump discontinuity. It could show that maybe it is continuous, but this first derivative is discontinuous. The first derivative could be continuous. The second derivative is discontinuous, and so on. So there are all kinds of things that's been delicately studied, and also the behavior of the curve of this thing near critical point. They satisfy some universality conditions. They are like of the form some x to the power half or x to the power 1/3. So there are some critical exponents. So there's a whole theory, critical exponent theory. And in this case, actually, it's extremely interesting to approach it. I mean, see what happens. You see the graph that I showed for phase transition. I mean, what happens to the derivative of the function as you approach the boundaries of the cut? I mean, there must be something very, very special as you approach the boundaries of the cut. I mean, this hasn't been investigated at all. I mean, there are a lot of interesting things that one should investigate in this model, and we are just at the beginning, very beginning. I mean, okay, but this was a very good question. Thanks, Thomas. Yeah.
I have a second question. Does it make sense to speak about a classical limit in this situation?
I don't know. I don't see how. No, not really, because you're really, I mean, the good thing is that you're already in the quantum domain by looking at matrices, Hermitian matrices. I mean, what gets closer to quantum mechanics than, energy operator of quantum mechanics being Hermitian operator? So you just have
quantum mechanics used to be called matrix mechanics for a while.
Oh yeah, there is something. Yes, that's right. That's right. But there is now this. There is something called matrix quantum mechanics, which is different. So it's a different thing. It's very much related to random matrix theory, and they used also this techniques of. They use also topological recursion, and also they use this bootstrap technique lately. So, no, to your answer, Thomas, I don't think one can take. Well, I hate to say no. I mean, because it's always a very bad idea to say no. I mean, to something.
Never say never.
You should never say no to an idea, whatever it is. I mean, no. I don't see any relation right now. Let me put it this way. I mean, but there might be some, who knows? I mean, I don't know.
One question more. What about symmetries? If your system has some symmetries, can you see these symmetries on the level of your matrix model and this random?
Yes, model? That's what exactly. No, that's again excellent question. That's what exactly Dyson did first in his threefold way. So he imposed some symmetries on the model. For example, there is this thing called time reversal symmetry. So time reversal symmetry is an anti-unitary, I believe, is an anti-unitary operator. It's a bit like our own J that commutes.
Anti-commutes with this, with this complex structure.
Yeah, with the complex
and the Hamiltonian, yes.
Yes. So this is this is called time reversal symmetry. And if systems have time reversal symmetry, I believe his argument was that you are in the domain of symmetric. Maybe quaternion.
Quaternions, yes.
The domain of quaternionics. So this is a third ensemble, which is GSE, Gaussian symplectic ensemble. Although it's quaternion, but there is also, of course, quaternion Hermitian group is related to symplectic group, and this is called Gaussian symplectic ensemble. So yes, there is this classification of these matrix models, random matrix models based on symmetries. But then there is also a very recent classification. I don't know if it has. So there is called tenfold way, and there's Kitaev. I don't know some. I don't know. I don't remember. Yeah, Kitaev has this more classification, kind of finer schemes. But I haven't seen any kind of reflection of that in random matrix theory literature for this. But that's for topological states of matter and for that theory, which is different. Topological phases of matter.
Mm-hmm. Mm-hmm.
And Kitaev periodicity, periodic table of matter. Yeah.
So I see Andre wants to ask a question. Andre Ludwig.
Yes, Andre, please. Yeah. Where is Andre? I don't see.
No, to thank the speaker. Are we not muted?
Andre Ludwig, do you want to ask a question?
No.
Okay.
We want to thank the speaker. We need to catch the bus, sorry.
Okay, thank you, Andre. Thank you, Ludwig. Nice
Okay, but Ludwig should stay because I need him for later on. So you can catch the bus, but please allow Ludwig to stay. Adam, do you still have another question?
Yes, I still have one. So my question is the following. Do you believe that after all, okay, I agree that quantum gravity is it would be extremely difficult problem, but after all, at the end, how do you feel that somehow one should also take and integrate over all possible geometries, meaning also that the algebra is a variable, or?
Oh yeah, that's that I don't know really. I mean, because in also quantum gravity there are two issues, right? You have metrics, and some people also think space-time also should be taken as a dynamical variable. So you have to integrate over all space-time, so that you then, as a result, you completely wipe out background from the picture if you do this, something like this. But no, I mean, we are. No, this is not anywhere near that sort of dreamland. I mean, I was really interested from mathematical perspective because it introduced some very nice, challenging mathematical questions. And I honestly got into this with the students because of my naivete. I mean, if I knew more about this, I wouldn't dare. I wouldn't dare to enter. But it was a lucky. It was yeah. I feel extremely lucky. I had Shahab, and now there are Nathan and Hamed working on this. So it's extremely lucky that he went to this Princeton school, and then he learned a lot of things, and we talked a lot. And of course, I mean, in my seminar also I was covering random matrix theory, but not to this effect, not this much. So, but yeah.
So I'm asking this question since for me this is a really very dramatic, very drastic difference between taking integral over all possible Diracs, which is already something very difficult, and after all trying to make sense somehow of the integral over all possible geometries.
You're right. Yeah, I mean, one of the things was, you see, there is this idea, I think due to Mark Riefel, that these matrices converge to S2. These matrices converge to S2. So I think the idea was to see, to sense that as n goes to infinity, actually in the eigenvalue, spectral distribution of the Dirac operator, although you are dealing with finite matrices, you will see some manifold behavior at the end. So you're really approximating S2. So this would be like some sort of quantum gravity on S2 or something. Now, I don't know what's the status of this like idea dream. I have to talk to people about this, but this was, I think, one of the things. And this you cannot approach using, commutative ordinary spectral triples, because if you have finite spectral triples, I don't think they would converge to S2. I mean, of course, I mean, there is always this idea that if you have a manifold and you you know, you have kind of mesh of points on the manifold, and you take finer and finer things, then maybe this combinatorial Laplacian will approach to the Laplacian and in the limit. But there are these ideas, but they are not they are very limited. And so non-commutativity here brings something to the table. Yeah, it seems really something new to the table. So this is I find it attractive, this idea of Mark Riffel, which was used by John and Lisa. Yeah.
John Barrett,
if I could, yeah, if I could comment the last.
Okay, thank you.
The last answer. There's some symmetry which rigidifies this limit. This fuzzy sphere is a limit of matrix algebras only because the presence of SU2 representations in all these matrices.
Yes.
So without this rigid symmetry, maybe
bootstrapping principle. This.
Yes. This is a kind of a bootstrap.
Yes, indeed. Okay. Yes, exactly. That's good to know. And in fact, these models, the action is unitary invariant.
Yeah.
The action is unitary invariant, both in terms of H and in terms of D itself. So these are really unitary invariant actions. I mean, I should be careful for one matrix model, but if you go to two matrix models, you have two things. Okay, so these are not in general. These are not in general unitary invariant. So the Dirac operator itself, I guess this is unitary invariant, for SUN, because you just use trace. On this space.
Okay. Anybody else? I don't see any raised hands.
I have still one small question, if I could, but I don't know.
Well, go ahead.
So my question is the following. In one of your slides, you have this, I don't know whether I would call it correctly, genus expansion, yes?
Yes.
And in the exponent, you had 2 minus 2g, yes?
Yes, g is the genus of the surface, yes.
Yes, so for g equals to 1, you get something which is independent from n. Is this somehow, I don't know, a critical behavior? What is the meaning? Is there any deep meaning of this fact, or it is just a coincidence?
No, I think this should be there. I mean, the thing that's really so that limit still has to be rescaled, I believe, by 1 over n2. So because it starts with n to the, so it was n to the power of 2 minus 2g, right? If g is equal to 0, you have this n2. But if you rescale by 1 over n2, then you get constant term, and the limit, that's what survives. All other terms, and this is called the planar limit. This is, by the way, is called the planar limit. And the name of that paper of Itzykson-Paris-Zuber and others is called, planar limits, planar diagrams, actually. That's the name of it. So yeah, that planar limit, it just corresponds to graphs that are maps that are drawn on a sphere, on the sphere, and that's the leading part. That's what gives you the higher corrections. They become important, but you have to understand them in each case in their own way. So the leading part is really for computing. For computing this correlation for computing moments, the first thing is just leading parts, which is.
And this power 2, so the square as a leading term is because of the dimension, because it's planar situation, yes?
The power of 2, yeah, because g is equal to 0. But I mean, if you there is also a genus expansion for a real. Ensembles, symmetric matrices. In that case, the power is 1. So I mean,
okay.
the reason you see 2 minus 2G because you're dealing with complex Hermitian.
I see. I see.
And I haven't seen this actually worked out. Maybe there exists also a genus expansion for the quaternionic case, but I haven't seen anything done. But maybe exists. I don't know. But yeah, in that case would be 4. So yeah, there is this parameter beta, which is equal to 1, 2, and 4, covering those 3 cases.
Okay, thank you. So I was asking this question because in those thermodynamical stuff, very often it is the case that these critical exponents are difficult to compute, to prove something about them is difficult, but there are some kind of heuristic arguments which somehow would give you a clue what this critical exponent should be.
Yes.
And this looks like something like this in this spirit. Well, thank you.
Yeah. So right. I mean, overall, you see what happens in this statistical mechanics and you know study of complex systems and this. Even some areas in random matrix theory as practiced by physicists, actually, I mean, there are a lot of interesting methods and ways of thinking about these things that are still not amenable to mathematical treatment. I mean, this is a huge subject for mathematicians. You know, I have this book by Talleyrand. It's called Spin Glasses, A Challenge for Mathematicians. It's like, I don't know, 500, 600, just amazingly difficult probability theory, you know, and this, yeah, I mean, Parisi got this Nobel Prize, you know, for his study of basically spin glasses, for a study of the spin glasses. And methods that Parisi has introduced are so, I mean, they are wonderful, they give results, but I don't think mathematically they are understood or they have been justified at all. So it's far away from
no, they are not.
Huh?
They are not justified mathematically.
They are not justified. Yeah,
no,
exactly.
No.
Yeah.
No, mathematics is not there.
Yeah, mathematics is not there. Exactly. I mean, that's what Richard said. Exactly. I mean, thank you, Richard. Yeah, exactly. They are not, and it poses very interesting challenges. So they are far ahead of us. I mean, in that regard. So they're far ahead of us. So.
You mean physicists, as usual?
Yeah, these physicists. I mean,
at least some of them.
Yeah, some of them. Yeah. I mean, these really visionary and ingenious methods that they introduced. I mean, like this Parisi, you know, I mean, Talleyrand, I mean, proves everything, I mean, in a very precise way, but I mean, he says that this is a big challenge. We don't know how to handle this. After, you know, I have his book actually here, so maybe I could show you. It's called The Spin Glasses, A Challenge for Mathematicians. That's the title of the book. That's the title of the book, yeah.
Great. Okay, I think it's time to wind it up. Just let me have one very quick naive question and one very quick simple-minded comment. So my naive question to MASOUD is, why is it not possible to measure the eigenvalues and the energy levels? Why only the difference? Could you just briefly tell me why?
Oh, because when atoms are excited, you know, they drop from one level to another. And what you see,
yes,
your photon wavelength or photon frequency that you measure is the difference of the two.
Yeah, that's I've got you. Yes.
Right, exactly. That's exactly like that was the so in neutron scatterings that they are called level. I mean, this was called level spacing. Spacing.
Yeah, I've got it. It's. Thank you so much. I needed this one word, which was the key. Could you please go back to your first slide?
My first slide. Oh, sure. Yeah. Okay, so let me just close this and let me go to my.
I mean, not the title page, but the first.
Okay, so I have to maybe go to another mode. So how can I?
Okay, so that's all right. So maybe I can speak without it. You see, when you talked about these Euler-Lagrange equations, this variational principle, a long time ago, I committed a paper about a toy model for the Einstein-Hilbert action.
Right.
And I find it fascinating to see this Palatini method of variation. So when you wrote this Einstein-Hilbert action functional, Well,
Right.
it depends on G, and you use some Levi-Civita connection to construct this action with scalar curvature. But you can write these expressions having your connection not being a Levi-Civita connection. And then when you keep your metric fixed and solve the Euler-Lagrange equations for the connection, it pops out that the Levi-Civita connection is a solution. So this is, I think, for me, a very beautiful example that that's not any superstition that you should use minimal action and Euler-Lagrange equations. That this is a very good principle for deriving not just physics, but even mathematics out of this minimizing principle. And this was a complete, toy model. This is just some matrices, so nothing serious. But it was really hard for me to write down what it means that a connection is metric compatible. Mimicking classical ideas just didn't work. So then I used this Palatini method of variation. This is a simple, high school calculation, and I could derive this metric compatibility condition, which is completely unusual. It's not something you would exactly expect. So this was just my small comment. And I think that it's time just for the final word to MASOUD.
Okay, thank you so much. Thank you so much to all of you.
Thank you so much. And
Thank you, MASOUD.
Thank you, Richard.
Thank
Thank
you.
you for being here. Thank you all. Yeah, thanks a lot.
Thank you, MASOUD. Thank you.